Good morning, friends. Welcome to TurboMachine classes. I am V. Sushant Kumar, Department of Mechanical Engineering, Angri Institute of Technology and Management, Belagavi. In today's class, we'll discuss about first and second law of thermodynamics applied to turbomachines. Before going to the discussion on this topic, I would like you to go through the definitions of basic thermodynamics, like what is system and types. Basically, we have three types of system: closed system, open system, and isolated systems. Okay, and what is the meaning of surrounding, and boundaries and types, what is heat, what is work, and first law of thermodynamics, very important. Okay, applied to closed system and applied to flow system. This is very important. We are going to use this concept in our further discussions here in this class. And what is enthalpy, what is internal energy, and second law of thermodynamics. We have two types of statements in that: Kelvin Planck statement, Clausius statements. So all these concepts, if you know, you will understand this class easily. So I kindly request you to go through all this before going to the video lecture, especially first law of thermodynamics applied to a control volume, because we are going to use this concept in understanding the turbo machines. Fluid that flows through the turbo machine, it always varies with time. There is always fluctuations, but when you consider over a long period of time, we assume that the turbo machine flow is considered as steady flow over a long period of time. Steady flow. Steady means what? There is no change with respect to time. Okay, so this is an assumption that we are going to make. Okay, otherwise there is always some variation, but if you consider overall a turbo machine, the flow is considered as steady. Okay, so this assumption will help us in applying the first law of thermodynamics to a open system, that is to a control system. Okay, now we can apply the steady state control volume equation. Okay, so turbo machine means any machine. Okay, either it gives power or it consumes power. There can be multiple inlets, there can be multiple outlets. Okay, so now I will consider only single inlet and single outlet. Okay, and let me write steady flow energy equation. Okay, which we have studied in first law of thermodynamics applied to open system. Okay, and let us see the uh, equation how it goes. Okay, so whatever equation I have written here, this is steady flow energy equation. Okay, from first law of thermodynamics applied to a control volume or open system. Okay, where Q is rate of energy transfer as heat across the boundary of control volume. Okay, control volume means what? Open system. Okay, so m dot refers to mass flow rate. Okay, so just m refers to mass flow. When I keep this dot over this m, this dot refers to rate. Okay, mass flow rate. Okay, this h1 enthalpy at the inlet, and v1 is velocity at the inlet. Okay, and g is acceleration due to gravity, and z1 is datum height. Okay, so h1 enthalpy v1 square by 2, it is a kinetic energy, and gz1 is potential energy at the inlet. Similarly, on the right hand side we have power output. Okay, due to the turbo machine. Let us consider, we are considering power generating turbo machine, so power output due to the turbo machine, and m dot is mass flow rate, h2 is enthalpy at the outlet, v2 square by 2 is kinetic energy at the outlet, and gz2 is potential energy at the outlet. Okay, so now we have written steady flow energy equation. In our previous video lectures in the static and stagnation properties, we have seen this expression. Okay, stagnation enthalpy H naught is sum of static enthalpy H, kinetic energy, potential energy. So here I am supposed to write H suffix I. Okay, but usually we drop this suffix I. Okay, if I just write H, it means that it is static enthalpy. Okay, so we have derived this equation, okay, in our previous classes, wherein stagnation enthalpy is sum of static enthalpy, kinetic energy and potential energy. So now using this equation, okay, so we can write steady flow energy equation, we can modify. Okay, steady flow energy equation as follows. So this is H, this is kinetic energy, this is potential energy. So I can replace these three terms with stagnation enthalpy H naught 1. So you can see here in this equation, okay, Q plus m dot, this whole h1 plus v1 square, h1 plus v1 square by 2 plus gz1 is replaced with stagnation enthalpy. Okay, similarly on the right hand side, equal to p plus m dot, this whole three terms h2 plus v2 square by 2 plus gz2 is replaced with stagnation enthalpy h naught 2. Okay, so now dividing this whole equation by m dot, okay, we get small q minus small w. What is this small q? Small q is nothing but q by m dot. Okay, heat transfer per unit mass flow through the control volume, and this small w is, it is p by w. Sorry, it should be p. Okay, please make the correction, p by m dot. Okay, work transfer per unit mass flow through the control volume. Okay, p is just work output. Okay, p by m dot is work transfer, okay, per unit mass flow. Okay, so now we get the equation, okay, q minus w is equal to h naught 2 minus h naught 1. Okay, so I'm going to take this p by m dot on the left hand side and h naught on the right hand side. Okay, so this is the equation that we get, q minus w is equal to h naught 2 minus h naught 1. This h naught 2 minus h naught 1, I can write it as delta h naught. Okay, so q minus w is equal to delta h naught, where this delta h naught is difference of stagnation enthalpy, okay, at the outlet and at the inlet. Okay, so this above equation, we can call it as this above equation is very important. This remember this, because in our next slides and in next classes, okay, while solving the problem, we are going to use this equation. So in the previous slide, we have seen the relation between heat transfer, work transfer and stagnation enthalpy. Okay, so now let's make some assumptions, valid assumptions. Okay, and let's see how the equation varies. You know that generally the turbo machines are well insulated. Okay, so if you go to any power stations, usually the gas turbines, steam turbines, so all of them are well insulated, and the velocity of the steam and gas that flows through the turbo machine is it's very high. Okay, the steam and gas turbines, the velocity flow, the heat, the time taken for heat transfer is very less. Okay, so you can assume it as heat transfer will be just 0.25% of work transfer. And as well as if you're going for incompressible flow liquids like water and oil, heat transfer even in them, okay, between the liquid to the outside environment, heat loss is negligible, as these liquids operate at room temperatures. Okay, and even if you are considering handling of warm liquids, the specific heat of these liquid is so high that there is very negligible change. So what is specific heat? Specific heat. So specific heat is amount of heat required to rise the temperature of a substance, okay, unit mass of substance, through unit uh, degree Celsius. Okay, suppose for example there is 1 kg of substance and you want to rise its temperature through 1 degree Celsius, then what is the amount of heat you need to supply? Okay, that is specific heat. So usually the specific heat of liquids will be high, so there is hardly any negligible temperature change. Okay, so assuming all this, okay, so we will neglect assuming all this, so we can neglect Q. Okay, so in the previous slide we have seen this equation, Q minus W is equal to delta H naught, where delta H naught is change in stagnation enthalpy between inlet and outlet. Okay, so if I neglect this Q, then my equation will reduce to delta H naught is equal to minus W. What is this W? It is P by m dot. Okay, so this equation has reduced to delta H naught equal to minus P by m dot. Okay, so energy transfer as work is numerically equal to the change in stagnation enthalpy of the fluid between the inlet and outlet of the turbo machine. Now let us see the expression for stagnation enthalpy. Okay, variation of stagnation enthalpy, what happens for two cases, one for power generating turbo machine and one for power absorbing turbo machine. In case of power generating turbo machine, wherein the turbo machine is generating power, it is using the energy available within the fluid. Okay, that energy from the fluid is converted into work as a shaft rotation. In case of power generating turbo machine, work is positive. Now if you look at this equation, W is equal to minus delta H naught, which we derived in just previous slide. This delta H naught is H naught 2 minus H naught 1. If the work has to be positive, then this H naught 1 should be greater than H naught 2 here. If the W has to be positive, then H naught 1 should be greater than H naught 2. Now what it means? H naught 1 is stagnation enthalpy at the inlet and H naught 2 is stagnation enthalpy at the outlet. So what is the meaning of, how can we analyze this? W is equal to H naught 1 minus H naught 2, and for power generating turbo machine W is positive. It means that stagnation enthalpy of the fluid at the outlet of turbo machine is less than the stagnation enthalpy of the fluid at the inlet of the turbo machine. So when the fluid is flowing through the turbo machine, its energy is utilized in converting into mechanical energy. Okay, so the enthalpy drops. In power generating turbo machine, the enthalpy of the fluid drops as it flows over the turbo machine. That's why at the exit of the turbo machine, the enthalpy of fluid is less. In this case, we'll call it a stagnation enthalpy. Stagnation enthalpy of the fluid is less at the exit of the turbo machine. That difference of enthalpy is converted into work. Now let's go to the second case, that is power absorbing turbo machine. In case of power absorbing turbo machine, the turbo machines will use power. In most of the cases, it is electrical power, and that power is converted into mechanical energy and that mechanical energy is further transferred to the fluid. It is just opposite of power generating. In case of power absorbing turbo machine, we are supplying power to the turbo machine, and that power is converted into electrical energy, and further that power is converted to mechanical energy, and further that mechanical energy is transferred to the fluid. So in case of power absorbing turbo machine, delta H naught is positive. Let us consider the same expression, delta H naught is equal to minus W. Okay, W is, if I take this negative sign on the left hand side, W is equal to H02 minus H01, H02 minus H01. So what it means is, if this right hand side, if it has to be positive, then H02 should be greater than H01. So how can you interpret this? H02 greater than H01. In case of power absorbing turbo machine, the stagnation enthalpy of the fluid at the exit of the turbo machine is greater than the stagnation enthalpy of the fluid at the inlet of turbo machine. You are supplying some energy to the fluid. Some energy is transferred. The mechanical energy of the turbo machine is transferred to the fluid in case of power absorbing. So some energy stored within the fluid when it comes out of the turbo machine. So its stagnation enthalpy is more than the inlet. The fluid that is coming out of the turbo machine, its stagnation enthalpy means the energy content in the fluid is more than the same fluid when it was entering into the turbo machine. Understood? I'll just summarize what we have discussed in this slide. In case of power generating turbo machine, stagnation enthalpy of the fluid at the outlet exit of the turbo machine is less than the stagnation enthalpy of the fluid at the inlet of turbo machine, and just opposite of that is for power absorbing turbo machine. In case of power absorbing turbo machine, the stagnation enthalpy at the exit of turbo machine H02 is greater than the stagnation enthalpy of the fluid at the inlet of turbo machine H01. Now let's look at the expression for work. Expression for work in terms of stagnation enthalpy, how the expression for stagnation enthalpy varies for different turbo machines. Let us consider the first case, turbo machine handling compressible fluids. The turbo machines handling compressible fluids. So in case of turbo machines handling compressible fluids, change in the head, okay, is very negligible. Okay, so changes in static head causes very negligible changes in enthalpy. Okay, so here we will neglect the head, that is GZ. So the expression will slightly change. W is equal to minus delta H naught. This delta H naught, it is stagnation enthalpy, sum of static enthalpy plus kinetic energy plus potential energy. So here we are neglecting the potential energy. So H naught I can write only as static enthalpy plus V square by 2, static enthalpy plus kinetic energy. Okay, so for turbo machines handling compressible fluids, static head causes very negligible change in the enthalpy, so we neglect it. Let us come to the next case, that is turbo machines handling liquids. Okay, in case of turbo machines handling liquids, effect of changes in potential energy are large. Okay, effect, if there is slight change in potential energy, its effect on enthalpy is significant. So we cannot neglect the potential energy term in case of the turbo machines handling liquids. And changes in internal energy are negligible. Okay, changes in internal energy are negligible, and we can neglect the internal energy here. And since we are saying it as liquid, we assume it as most of the cases incompressible, so that density remains. the constant, density remains constant. So the expression for the work done expression, W is equal to minus delta H naught. This expression for this H naught slightly changes for the turbo machines handling liquids. So what is this H naught? H naught is minus delta P by rho. Okay, P by rho plus V square by 2 plus GZ. So this is the expression for work transfer for the turbo machines handling liquids. So how we got this equation? It has been discussed in my second video lecture under the topic static and stagnation properties. You can go there and refer the derivation. Here I am directly writing the expression. Most of the turbo machines will have two types of blades. One is stator blade. Stator blade means it is fixed, it doesn't rotate, it doesn't move. And second one is rotating blade or rotors, which moves. Okay. In case of stator blade, we know from the definition of turbo machines what we have studied, the definition, the energy exchange takes place due to dynamic action. Okay, dynamic action between the fluid and rotating element. Okay, so here if you look at the sketch, stator blades, it is not rotating, it is fixed. This 1 and 2, 1 is the inlet of stator blade and 2 is outlet of stator blade, and 3 is inlet of rotating blade and 4 is exit of outlet of rotating blade. So from the definition of the turbo machine, the energy exchange between the fluid and rotating element takes place due to dynamic action. Okay, so where the dynamic action is taking place? Dynamic action is taking place in the rotating blade, not in the fixed blade. Okay, dynamic action takes place through the exchange of momentum between the rotating blades and the flowing fluid. Okay, so it thus follows that all the work is done when the fluid flows over the rotor blades, not over the stator blades. Okay, since stator blades are fixed and rotor blades are moving, rotating, so all the energy exchange takes place in the rotor blades. Understood? Okay, so in case of stator blades, the stagnation enthalpy will not change. H01 is equal to H02 here. In case of stator blades, the enthalpy of fluid will not change, it remains constant. H01 is equal to H02, means stagnation enthalpy of the fluid at the inlet is equal to stagnation enthalpy at the outlet of the stator blade. So whatever enthalpy change occurs, that occurs in the rotating blade. Okay, if it is power generating turbo machine, the enthalpy goes on dropping as the fluid flows over the rotor blades. If it is power absorbing turbo machine, the enthalpy of fluid goes on increasing as the fluid passes through the turbo machine. Okay, the summary of this discussion in this slide is, usually in turbo machines we will be having two types of blades, stator blade and rotor blades. In stator blades, there is no change in energy of the fluid. Enthalpy remains constant in stator blades. Keep it in mind. Don't confuse. Okay. Whatever enthalpy changes, whatever energy exchange takes place, it takes place in the rotor blades. Very important. Okay. Very important difference that you have to remember. Okay. Then you may ask me a question. Then what is the function of stator blade? The function of stator blade is, it will guide the fluid, okay, in such a way that the fluid enters into the rotor blades smoothly. It just guides the fluid, okay, so that the fluid enters into the rotor blades smoothly. That is a function of stator blades. I hope that you understood what happens to the properties of the fluid in stator blade and rotor blades. Let's take up one simple example to understand the concepts of application of first and second law of thermodynamics applied to a turbo machine. Let's go to the example. A turbo machine handling liquid water is located 10 meters above the sump level and delivers the liquid to a tank 20 meters above the pump. The water velocities in the inlet and outlet of the pipes are respectively 3 meters per second and 5 meters per second. Find the power required to drive the pump if it delivers 100 kg per minute of water. Okay, so here you can look from the sketch. So there is a pump here. Okay, so this pump is at a height of Z1, that is, it is at a height of 10 meters from the sump. Okay, so this is the sump. I am taking the water level in the sump as the reference datum. Okay, the pump is 10 meter above the sump. Z1 is equal to 10 meter, and the delivery point, that is H reference datum 2, okay, is at a height of 20 meters from the pump. So Z1 is 10 meters and Z2 is 20 meters. Okay, so now the velocity of the fluid in this pipe, it is 3 meters per second, that is V1, and the velocity of the fluid here, it is 5 meters per second. And he has also given the mass flow rate. What is the mass flow rate? It is 100 kg per minute. Okay, for every minute 100 kg of water is transferred. So here we have been discussing in class how to solve problems. So whenever any problem is given in the examination, first you go through the problem, read it twice, thrice. Then very important is you have to write the given data. What is given? Okay, here he has said water, so the density of water is 1000 kg per meter cube. Okay, we have to remember this. And Z1 is 10 meters, Z2 is 20 meters, V1 is 3 meters per second, V2 is 5 meters per second, and mass flow rate is given as 100 kg per minute. So what are the assumptions that we are going to make here? So first one is liquid water, we consider it as incompressible, so the density remains constant. And second one is enthalpy is a function of density alone and is independent of temperature. Okay, now let's go to the solution part. We know the expression for the work done. So here we are not going to neglect the Q term. So in previous cases we were just taking different cases, okay, and we were seeing the expression, the relation between work, heat and stagnation enthalpy. Okay, so here I have directly modified it and I have taken Q on the right hand side. W is equal to Q minus delta H naught. So this delta H naught, it is written as P2 minus P1 by rho plus V2 square minus V1 square by 2 plus G Z2 minus Z1. Okay, it is nothing but P by rho. In the previous slides we have seen expression P by rho plus V square by 2 plus G Z1. Since we are considering inlet and outlet, okay, so we are writing it as P2 minus P1 by rho V2 square by minus V1 square by 2 G Z2 minus Z1. Okay, so now this P1 P2 terms will cancel out. How? I'll tell you. Okay, so look at the sump here. Sump is open to atmosphere. Okay, and even the overhead tank, it will be open to atmosphere. So the pressure in the sump and the pressure in the overhead tank will be same, atmospheric pressure. So the P2 P1 will get cancelled. Okay, very important. Okay, very important, why it get cancels. And V2 is 5 square, okay, and V1 is 3 square, okay, plus G is 9, acceleration due to gravity 9.81, Z2 is 10, and Z1 is, sorry, Z2 is 20 and Z1 is 10. You may ask me a question here, there is a minus sign here, but there is a plus sign here. We are measuring the height taking this pump as a reference. Okay, now I'm measuring it downward, so I rate it as minus 10, whereas I'm measuring it in opposite direction, so I rate it as plus 10. Got it? So my answer expression for work done will be 302.3 joules per kg. 302.3 joules per kg. So for to transfer every kg of water, we need 302.3 joules of energy. Okay, so now the total power required is mass flow rate into work done. Okay, mass flow rate here it is given as 1000 kg per minute. It is given per minute. We need to convert that into second. So in 1 minute we have 60 seconds. So 100 per 60 seconds. That's what is written here. 100 per 60 means I am converting 100 kg per minute into 100 kg per second into 302.3. So total power required is 503.84 watt. Power required is 503.84 watt. So this is the ideal power. The actual power needed to drive the pump will be larger than the calculated one. Okay, due to losses in friction in the pipes, entry, exit losses and leakages. Okay, this is whatever 503.84 watt we have got. This is the ideal case, but in actual pump, the power required will be greater than this, because always there is a friction and there will be some leakage losses and there will be some losses at the entry and exit of the pump. So actual power required will be greater than this. I hope that the concepts are clear with this example. In today's class, we discussed about expression for steady flow energy equation, and using this steady flow energy equation, we try to understand the turbo machine in terms of work, heat, and stagnation enthalpy expression for that. And we also studied the modification in this relation, work, heat, and stagnation enthalpy for different types of turbo machines, like turbo machines handling compressible fluid, turbo machines handling liquids, power generating turbo machine, power absorbing turbo machine. So we try to understand the relation between work, heat, and stagnation enthalpy for all these types of turbo machines. And we also understood the differences. We also discussed what are stator blades and rotor blades and what's their function and how the energy action takes place. Okay, there is no energy action taking place in stator blade and all the energy action takes place in rotor blade. And we try to understand all these concepts considering an example, very simple example. I hope that you have understood the concepts, that is first and second law of thermodynamics applied to turbo machines. If you find any difficulty, you can always contact me. Thank you for watching the video.